actually a central nervous system depressant, wherein one of the drugs is actually highly active and the other one is not. So in stereoisomerism also we talk of two types of isomerisms. As I said earlier, we have configurational isomerism and we have conformational. Again, the conformational isomerism is of little less significance again for the pharmacist, because this involves the isomerism due to rotation around a CC bond, and the configurational would tell the exact configuration of the particular molecule. And in configurational isomerism we have two types. We have geometrical isomerism and then we have optical isomerism. So this is geometrical isomerism we are talking right now. Geometrical
our purpose, geometrical isomerism is important, and we will discuss only geometrical isomerism.
No, also the optical, because optical isomerism is equally important. The reason being, there again depending upon the optical activity of the molecule, the drug action is decided basically. So geometrical isomerism is caused by different arrangements of the groups around a rigid framework. And generally this rigid framework would involve a double bond. We know that.
What do you mean rigid framework?
Rigid will mean, there will not be a rotation possible around that particular bond. See, we have CC bond, you've seen, and if we had models we could show it easily. A CC bond can be easily rotated, whereas if we have a double bond it becomes difficult, the rotation is restricted, and that is what we mean by rigid framework. And if we take an example of 2-butene, we can properly, I think, rationalize this particular type of isomerism. And if we look into the structure of 2-butene, we'll see that in one of the butenes, we have the methyl groups which are, if it is the plane of the molecule, we have methyl groups which are placed on the same side of the plane of the paper, or the slide which you are seeing, or else it can be, the methyl groups can be arranged just opposite to each other, as in the second case. So when they are on the same side of the plane, we call it as cis structure, and in case of 2-butene we'll call it cis 2-butene. And when they are against each other, then we call it trans 2-butene. So the way we've taken 2-butene as an example of a geometrical isomerism, which we call as cis-trans isomerism also, we can take a number of examples which have double bond in between the two carbon atoms and try to see which one is cis and which one is trans. And also, sometimes we are not always categorizing them on the basis and naming them by cis and trans, because not always we have a hydrogen atom which is opposite to, or which are on the same plane. For this cis isomerism, we have two hydrogen atoms and two methyl groups, and when these hydrogen atoms are on the same plane or towards the same side, we call it cis. But what happens when we don't have a hydrogen? Instead of hydrogen, if we have any other group, still there will be a geometrical isomerism which will exist. And in that case we have a different nomenclature, though we have not put it on the slide, but you should know that that type of nomenclature we use as ENZ. Yeah. So the E1, we are representing the E nomenclature goes for the trans and the Z goes for the cis. And the way we are trying to kind of see the groups here, similarly we see for the E and Z isomerism also. Well, optical isomerism actually is the most significant for all pharmacists, because this is the one which differentiates one highly active drug from a non-active drug. And optical isomerism is basically shown by the molecules which have a chiral carbon in them. Chiral carbon, we mean that the carbon which different 4 groups are attached. You know that carbon is tetrahedral in nature, and when the 4 groups of the tetrahedral carbon are different, then we say that the carbon atom is chiral. And only those molecules which have a chiral carbon, they will show optical activity. And by what do we mean by optical activity? Optical activity is basically when the molecule in solution has a property of rotating the plane polarized right to either of the direction, like it can rotate the plane polarized right to the right or to the left, and depending upon whether it is rotating it to the left or right, we call the molecules as dextro or levorotatory. Dextro when they rotate the plane polarized right to right side, and levo when they rotate it to the left side. This is how we talk of optical isomer. And when there are these molecules, there are two isomers, one will be a dextro, another will be levo, we say that this molecule exhibits optical isomerism, and the isomers are said to be the optical isomers. And the absolute configuration for these optical isomers is given by R and S nomenclature, wherein R is for rectus and S is for sinister. So there are actually different set rules by how we assign these configurations, and by how we come to know of the absolute configuration of that particular optical isomer. Let us see how do we do this. As we've said that the enantiomers are of these two types, and when we want to assign, then what do we have to do? Basically, just concentrate on this molecule. What do? We have a chiral carbon here, and we have 4 groups with us, and the 4 groups have to be numbered in such a fashion. First of all, before numbering, you should be very well versed with the CIP rule for this. CIP rule was given by Khan, Ingold and Pralog. These 3 scientists together, they have made a set of rules by which you assign a priority to the 4 groups which are attached to the carbon atom. So on the basis of
there are concerned blocks for them.
Exactly. You have to look into some other blocks also. Maybe
in the same block. In the same block,
the CIP rules are given also, and also you can look into any organic chemistry which will give you all the rules slated into it, and these are more or less based on their atomic sizes. This goes by the periodicity of the elements. So what do is you assign the priority numbers to the groups, and what do? The next stage is that you put the least priority group at the back, which is pointing back to against you, away from you, and put rest of the molecules in front of you. Suppose this molecule, you have prioritized the groups, you have kept the first one at behind your scene, in the sense that which will not come towards you, and rest of the molecules you have assigned the priority numbers 1, 2, 3, and then see whether starting from the lowest priority to the highest one, you have to see where does the rotation go. If the rotation goes clockwise, you call it a rectus configuration, whereas when it goes anti-clockwise, you call it sinister, as shown here. If the priority is the other way around, this one is clockwise, of course, 1, 2, 3, you can see that the rotation is 1, 2, 3, and this is clockwise rotation, this is rectus, and if it is the other way around, that is from 1, 2 and 3 anti-clockwise, we call it as the sinister. I think this is grossly about the stereochemistry of the molecules which are involved with with the molecules which are used as drugs also.
Okay. Thank you.
Thank you.